start recording. I have two presentations for you here, for starters, because, well, first we have a word from our sponsors, obviously, and after that I'll be giving a little bit of an introduction to the general area of hardware abstraction layers that we will be talking about today. So I'll try to do like a very short run through of what's up, so those who haven't worked so much with embedded can kind of know what's up. So first, I'm here representing Tampere University and especially the SoC Hub project. This slide has been on screen for a while, so hopefully you had the time to mostly read what's going on. So to summarize briefly, it's a multi-year project at the university. I think there is no official news, I believe, on the actual length at the moment, but there may or may not be an extension to the project. So it may or may not continue until the end of next year as well. But other than that, yeah, we are on the final or second to final year of the project, and the main point of the project is that our university manufactured new SoCs, one per year, an entire SoC from mostly open source components and some components by companies. At the university we have a lab of about 60 people, including people from companies listed at the bottom, and from the university, and yeah, we do the design from pulling up open source hardware components, integrating them together, and then doing some software for it. And that's that. It's a pretty big project, and I think it's a pretty cool project. And yes, we have some Rust software involved with the project as well, so that is why I am here also. So here's the overall schedule. So we started in 21. I think I got involved at that time also in the beginning of 22. So the summary here is that we have made some chips, and we are maybe we have a fourth tape-out coming up as well. So we've made 3 chips. First row we have the ballast chip pictured here. After that we made 2 little smaller chips. These chips called Tackle 1 and Tackle 2, which are almost the same, doing some A/B testing, let's say, with different kinds of SoCs. And after that we did the third one, the head sail, which is like, I would call it a rerun of ballast, but with some new components, and maybe making some parts of the design saner, and yeah, trying out new stuff. So we are currently pretty close to the tape out of that chip, so we've been really busy this spring and summer, like checking out that everything is working and so forth. Yep, and coming up is the sample testing. Oh, I know this. Yeah, never mind. Right, so what's currently going on? Tackle sample testing, and yeah, verifying the head sail and whatnot. So for the rest of the introductory presentation, I have some cool pictures of the SoC. Nothing very informative, but maybe it acts as proof that the chips exist and we made them. And yeah, so that's it's a success to some degree. Yeah, so just cool pictures. That's how it looks like inside the. There's stuff on top of it, but yeah, maybe important. The ballast is really small in center of the chip, and then we have this wiring that takes all the space, and then we put that into the PCB, connect it to all the peripherals and all the interfaces, and then we start programming it and making cool stuff with it. It's a pretty typical lab setup, I guess, and yeah, that's that for the introductory presentation. So SoC Hub and Tampere University are hosting us here today. They have paid for the pizzas, paid for the sodas, and they are making this space available for us. So I thank the project, and I hope you have a good time today. Yeah, sure. Go ahead.
Can you tell us which process node are you targeting?
Which process node? I am a software engineer. That's a good response to that question, I guess. It's the numbers are escaping. It's like, I think it's 15 nanometer is what the question what you are. Yeah, pretty big, and then. Yeah, it's like not quite state of the art, but like the previous state of the art. Yeah, I think that's. I'm pretty confident in my answer that is the right number, and we are of course investigating possibility of targeting smaller nodes. But the nice thing about this is that it's inexpensive to do so. We don't mind if it's kind of big on chip, and we can do our testing on it and. But we do hope that we learn to do the smaller nodes as well, so it's mostly a question of funding. Sure, go ahead.
What's in the SoC? Is it like ARM4 or RISC-V?
Oh yeah, it's RISC-V. That's pretty big and pretty important, I guess. Also from a software point of view, it's a very interesting platform to develop for. It's very different from the average ARM. And, I think we'll hear more about RISC-V software today. Yeah. So I can quickly comment on that. Yeah, well, RISC-V is cool. We have this open ISA, so we can we can do this sort of stuff that we just we have on GitHub. Effectively, we have processors on GitHub. We can pull them, do the design, ask for somebody to fabricate them and send them to us, and no. We don't have to pay anyone for it, and that's what companies can also do. And it looks like it could really change how these sorts of projects are run. It changes the entire embedded systems landscape, and maybe soon we can even have some desktop computers built on RISC-V. It feels like. Go ahead. When are the chips fabricated? Where? I think these. No. I know they are made in Taiwan mostly, though, or that's where the main part of the manufacturing is done. So, cutting the silicon wafers and rendering them, or whatever you say, and then those are sent to, I believe, Germany, and there they do some part of the process, and then we also have some facilities at our lab. And I think the PCBs are done at our lab, so. We get the ballast chip, for instance. We get it from abroad, and we put it on our own PCB and do the connections. And yeah, so for ballast, for instance, we have something like 50 instances, so 50 samples, 50 PCBs with 50 chips, SoCs, and yeah.